Okay, so we have already seen the application of Dalton's law, Amagat's law, and Gibbs Dalton's law. So in today's class, we will see a couple of examples about that deals with adiabatic mixing. Okay, so in this particular example, two vessels A and B, both containing oxygen, are connected by a valve which opens to allow the mixing of two streams. Before mixing, the following properties are known. So vessel A and vessel B, they have given you the conditions. So the pressure is given for both the vessels. And if you look at vessel A, what is given is the number of moles. So Na is given. Okay, so what is given to you is Na. And if you look at vessel B, what is given to you is the mass. So that is Mb, M suffix B. Okay, so what is given here is M suffix B. Okay, so temperature of oxygen after mixing reaches to 27. So that is the final equilibrium temperature. So now they're asking us to find the final equilibrium pressure and the amount of heat transferred to the surroundings. Okay, so they want us to find the final pressure and what is the heat transferred to the surroundings. Okay, so heat transferred to the surroundings. We are supposed to find out. Okay, so you can find out the mass, total mass after mixing, because in this particular case, what is given to you is one is given a number of moles, the other one is given in the mass. Okay, and whichever is convenient you can use, because it is ideal gas equation of state, and either you can use PV equal to MRT, or you can use NRU into T. So whichever is convenient to you, you can use both these relations. Okay, in this case, we have to use both the relations, but we can stick on to one permanently. Okay, so if you look at this particular vessel, the pressure is given, the temperature is given. Okay, so we can't use MRT for this particular vessel A. So temperature is given and the number of moles is given. The value of Ru is known to us 8314.4. So you can find out the value of Va. Okay, so once you find out the value of Va, okay, then you can use that to get the value of Ma. Uh, uh, Not necessarily, because Ma you can straight away get from, because what is given to you is oxygen. So oxygen, you can use the formula, you can use the relation number of moles equal to mass by molecular mass. So mass will be number of moles into molecular mass. Molecular mass of oxygen is 32. So 32 into 0.5 will give you the mass of oxygen in vessel A. So you can find out Va. And similarly in vessel B also you can find out Vb, because your mass is given, your pressure is given, your temperature is given. R of oxygen you can find out using Ru by M, 8314.4 divided by 32. So you can find out R. So that will give you the volume of the oxygen in vessel B, Vb. So in both the cases, so if you are able to find out MA and MB, so if you are able to find out MA and MB, now you will be able to know total mass of oxygen after mixing, because both of them are mixing. So the total mass after mixing you can find out. So that is what is shown here. The total mass is shown to you. The total volume is also shown to you, because you can add the volumes when both the volumes are mixing together. You can add the volumes. Okay, and the final temperature is also given to us. If you look at this problem, the final temperature is 27 degrees centigrade, which means 300 Kelvin. Now that you have found out the total volume of the mixture, the total mass of, sorry, it's not mixture, the total volume of oxygen, the total mass of oxygen, and the temperature, final temperature of oxygen is also given to you in the problem. And it is possible to find out the value of R using Ru by molecular mass of oxygen. So now in the relation PV equal to MRT, only V is missing. Sorry, P is missing. So you can use P equal to MRT divided by V. All these values are total values, the final values, and that will give you the final equilibrium pressure. So you can find out the final equilibrium pressure, which is 11.86 bar, and amount of heat transferred to the surroundings. In this particular case, it is just mixing, so work done is 0. Okay, so your Q is simply equal to delta U, which is mCV into T2 minus T1. And CV, you can use the relation R by gamma minus 1, and you can get the value of CV. R is known to us, this 259.83. If you look at the previous slide, 8314.4 divided by 32. So that is 259.83. The R value is constant. In both the cases, R is both the cases, the gas is oxygen. So your R value is 259.83. Okay. So you are able to get the value of CV, and just like we saw in the previous session, you can find out U1 using the relation MaCVTA plus MbCVTB. Before mixing, you can add up the internal energy of oxygen in vessel A and the internal energy of oxygen in vessel B. This we are doing theoretically. Okay, and U2, it is mCV into T, that is after mixing. You know the final mass of oxygen, you know the final temperature of oxygen, and you know the final CV of oxygen as well. Once, because R is fixed, CPCV is also fixed, gamma is fixed. So CV is going to be same for before mixing and after mixing. So CV value is 649.58 in both the cases. So here also you use 649.58. Here also you use 649.58. And this is applicable because in both the vessels you are having oxygen. Maybe in the problem that you may need to solve, in the question that you face, if one vessel has got oxygen, the other vessel has got nitrogen, then this CV will be different. Then this CV will be Xi into CVI. So what is the mole fraction of oxygen multiplied by CV of oxygen plus the mole fraction of nitrogen into CV of nitrogen. So that we have seen already. So that is how you should be able to find out U2. So Q is equal to U2 minus U1. So that gives us minus 227.68 kilojoule. Okay, a simple problem over here. Steps are lengthy, but there is nothing complicated here. Simple equations. Okay. Example 9. A vessel of 1.5 meter cube capacity contains oxygen at 7 bar and 40 degrees centigrade. The vessel is connected to another vessel, 3 meter cube capacity, containing carbon monoxide at 1 bar and 15 degrees centigrade. A connecting valve is opened and the gases mix adiabatically. Calculate the final temperature and pressure of the mixture, change in entropy of the system, and they have given you CV bar 21.07 kilojoule per kilomole Kelvin. CV bar for carbon monoxide is 20.86 kilojoule per kilomole Kelvin. So because they are using CV bar, it is better that we represent our equations in terms of moles. Okay. So what is given to us is the volume of the vessel comprising oxygen. So volume of oxygen is 1.5 meter cube. And the pressure of oxygen is 7 bar. Okay. And the temperature of oxygen is 40 degrees centigrade. So if you add 273, this is going to be 313 Kelvin. So this is going to be volume of the carbon monoxide. And this is going to be pressure of carbon monoxide. And this is temperature of carbon monoxide. And they have given you the CV value for oxygen, CV of carbon monoxide, sorry, CV of oxygen. And this is CV of carbon monoxide. These are all the given values. It is similar to the previous problem. In the previous problem, both the vessels contained oxygen. Now one vessel is containing oxygen, the other vessel is containing carbon monoxide. Okay. Here, what is not given to you is the final temperature. Okay. So if you remember in the previous problem, we used the relation MA. So in this case, it would be M of O2. So since we are using CV bar, instead of N, let us use N. N of O2 into CV bar O2 into temperature of oxygen plus N of carbon monoxide into CV bar of carbon monoxide into temperature of carbon monoxide. This is equal to the total number of moles multiplied by CV bar of the mixture multiplied by the temperature of the mixture. Okay, in all this, what is known to us is the CV bar of oxygen, the temperature of oxygen, CV bar of carbon monoxide, and the temperature of carbon monoxide, and that's it. That is all that is known to us in this particular equation. Okay, what we require is number of moles of oxygen and number of moles of carbon monoxide. Is it possible to find out that? So P of oxygen into V of oxygen using the ideal gas equation of state equal to N of oxygen into Ru into T of oxygen. Okay, so this pressure is given to us in the problem, this volume is given to us in the problem, this T of oxygen is given to us in the problem, Ru value is known to us, so it is possible to find out the value of N of O2. Similarly, you can write P of CO into V of CO is equal to N of CO multiplied by Ru into T of CO. In that case also, the pressure, volume, and temperature is given to us in the problem, and Ru value is known, so it is possible to find out the number of moles of carbon monoxide. Okay, so you can write down the same equation replacing the subscripts oxygen with carbon monoxide. So that will give you N of CO. So now after estimating the values of N of O2 and N of CO, that is also known to us. So this small n is nothing but N of O2 plus N of CO. The total number of moles is nothing but N of O2 plus N of CO. And if I have to find out the CV bar of the mixture, if you remember, Gibbs-Dalton's law tells us CV bar of the mixture is equal to summation of Yi into CVI bar. If it is simply CV, it will be summation of Xi into CVI. Because it is CV bar, it is summation of Yi into CVI bar. Okay. So now you have to find out the value of Y of oxygen and Y of carbon monoxide. So Y of oxygen is nothing but N of oxygen divided by the total number of moles. So N of oxygen divided by N. And Y of carbon monoxide is N of carbon monoxide divided by N. N of carbon monoxide divided by N. Okay. And so your CV bar will be Y of oxygen multiplied by CV bar of oxygen plus Y of carbon monoxide into CV bar of carbon monoxide. Okay, so that will give you CV bar. So now you will be able to estimate the final temperature of the mixture. So now you can estimate the value of T. So that will give you the final temperature of the mixture. Okay, and they are also asking you to find out the final pressure. Now you know the final temperature, and it is so because both of them are mixing together, your total volume will be volume of oxygen plus volume of carbon monoxide. Okay, already final temperature is known. Final temperature we have estimated just now. So final volume is known, final temperature is known, and the total number of moles N is known. So you can simply use the relation P equal to N RU into T divided by V. And all these values are known to us. RU is also known. So N is known, RU is known, T is known, V is known. Now you can find out the final pressure of the mixture. And change in entropy. So for change in entropy alone, you have to find out what is the change in entropy of oxygen, and you have to separately find out the change in entropy of carbon monoxide. Okay, so change in entropy of oxygen, we usually write mCv into ln of T2 by T1 minus or ln of V2 by V1. So in this case, because we are using CV bar, you can write it as N of oxygen multiplied by CV bar of oxygen into ln of T2 by T1. In this case, T2 is the final temperature, T1 is the temperature of oxygen. And if you take R is going to be R of oxygen ln of V2 by V1. V2 is the final volume, the total volume, 1.5 plus 3, 4.5 divided by the initial volume, which is 1.5. And similarly, you have to estimate delta S of carbon monoxide also separately. So if you want, I can write for this alone, and similarly you can write for carbon monoxide also. So N of oxygen multiplied by CV bar of oxygen into ln of T2 by T1 is T2 is the final temperature T, T1 is the initial temperature, which is nothing but the temperature of oxygen, minus, we usually use R, but since we are using number of moles, it will be Ru times ln of the final volume is V, the initial volume is volume of oxygen. Okay. So in this way you can do it. And there should be an N here, N of oxygen into Ru to balance the units. Because here you have kilomole multiplied by joule per kilomole Kelvin. So kilomole will get cancelled. So if you don't write N over here, you will have joule per kilomole Kelvin. So in the denominator, there will be a kilomole. So you have to multiply it with NO2. Okay. Similarly, you can do for carbon monoxide also. Then add up together, you will get the change in entropy. Okay. So that is how it would have been solved. So if you look at it, so they have found out the number of moles of oxygen, number of moles of carbon monoxide. Okay. In the previous problem, here you can see that two vessels are connected by a valve. Okay. And nowhere in the problem it is mentioned that the mixing is adiabatic. Okay. So what we did was we added up this. U1 was, we added up this U1 for vessel A and vessel B, and we equated it with the final internal energy. Okay. Whereas in this particular case, in this particular problem, they have said it explicitly that the gases mix adiabatically. Okay. So so in this case, there is no heat interaction with the surroundings or with the system. So what they are saying is, so for adiabatic mixing, before and after mixing, your internal energy is going to remain the same. As I told you, there can be a increase in temperature or a decrease in temperature to attain the equilibrium temperature within the gases that contribute to the mixture, but the internal energy is not going to change because it is still the same gases. A simple example could be there are two people, person A and person B. Person A has got 50 rupees. Person B has got 25 rupees. Okay. And now they are going to put that amount into a common account. Okay. So person A is giving 50, person B is giving 25. So the total amount is 75. Because this person A or person B, he did not spend his amount somewhere else. He's putting the total 50 in the account and 25 into the account. So now if you look at the initial amount each of them possess, if you add it, so that is 50 plus 25, 75. The final amount that comes into the account is also 75. So similarly, your internal energy in vessel A and internal energy in vessel B, if you add it, that will be equal to the internal energy after mixing. Okay. So if you go and do this, this is also a way to get the result. And here, I think I have done something wrong here with reference to the table, because NiCVI into Ti, hold on for a second. So what we have done here is N of oxygen into CVI of oxygen into Ti. That is what is this one. So why don't we check this and see how our result turns out to be? Okay. And this is N of oxygen into CV, N of carbon monoxide into CV of carbon monoxide into T of carbon monoxide that is available. So what I have written on the table here is wrongly conceived. Okay. So I think this value and this value which I have written doesn't match with this NiCVI TI. Okay, so let's leave that and let's check if we are getting the same answer 307 Kelvin with reference to what we wrote in the previous slide. What we wrote in the previous slide was N of oxygen into CV bar of oxygen into T of oxygen plus N of carbon monoxide into CV bar of carbon monoxide into T of carbon monoxide is equal to N CV into T. Okay. So let's see if we are getting the same value here. Okay. So N of oxygen here is 0.40, 4035. Let me take it as 0.40. CV of oxygen is 21.07. T of oxygen, how much was it? 40 degrees centigrade, which means 313 Kelvin. Plus N of carbon monoxide here is 0.13, let's say 1253. So let me take it as 0.13. CV of carbon monoxide is 20.86. and the temperature here is 15. 15 means 273 plus 15, 288. And then we have to add 0.13 plus 0.40. 0.13 plus 0.40 is 0.53. So we have to find out yi. Yi is so 0.40 divided by 0.53. So that is 0.75. So 0.75 is for oxygen. So it should be 0.25. 0.13 divided by 0.53. So this is 0.25. Obviously, it should be 0.25. Okay, so yi CDI bar. Yi CDI bar. So 0.75 into 21.07. So that gives you 15.8. And 20.86 into 0.25. So that gives you 5.2. So the total is 15 plus 5 is 20. So that will give you 21. YI bar. So that is 21. So what we have here as CV is 21. And now the equation is complete. So if you can find out the answer, so it is 0.4 into 21.07 into 313 plus 0.13 into 20.86 into 288 divided by 0.53 times 21. It's the same answer. That's correct. So your temperature is 307 Kelvin. So I was just framing the table from the values that were given in the book. So I have wrongly conceived this column. Sorry about that. So this should have been U1 and U2. U1 comprises both oxygen and carbon monoxide, and U2 comprises the mixture of oxygen and carbon monoxide together. U1 is oxygen alone and uh, carbon monoxide alone added together. Okay, so when they say U2 equal to U1, this U2 is after mixing, this U1 is before mixing. So it is both one and the same. Both example 8 and 9, it is one and the same. So we are getting the same value as the final temperature, which is 307 Kelvin. Okay. And they are asking you to find out the change in entropy. So you can follow the same procedure as we have done before for delta S of oxygen and delta S of carbon monoxide, and you can get the answer. And I think this should be a minus. This is not plus, this is supposed to be minus. So that will give you the total change in entropy. Okay. And you will see one more example. I think this is the last one. At steady state, 100 meter cube per minute of dry air at 32 degrees centigrade and 1 bar is mixed adiabatically with a stream of oxygen at 127 degrees centigrade and 1 bar to form a mixed stream of 47 degrees centigrade and 1 bar. The kinetic and potential energy effects are negligible. Determine the mass flow rates of dry air and oxygen, mole fraction of dry air and oxygen, time rate of entropy production. This entropy production is something which we have to look into. I think the rest will be very simple for you. So you have two entries and one exit. Okay, and what they are saying is the dry air is entering, or it is having a volumetric flow rate of 100 meter cube per minute, so that is V1 dot, and the temperature at the entry is given, and the pressure at the entry is given. So this is for dry air. And then they are giving the temperature of oxygen. So let me say T2, and the pressure of oxygen, which is maintained at 1 bar. So the pressure remains the same here for all the three. Okay, so it is taking place, this adiabatic mixing is taking place at constant pressure. So you have the final temperature and you have the final pressure. And what is given to you is dry air. So the constituent here is dry air, and the constituent for the second stream is oxygen. So for oxygen, you know the molecular mass is 32. For dry air, it is 28.97. So that is something you should remember. Molecular mass of air is 28.97. So, but that is not necessary because you know that R of dry air is going to be 287. So molecular mass you need not worry about. So R equal to 287. Okay, the first thing they are asking us to find out is the mass flow rates of dry air and oxygen in kilogram per minute. Okay, so what you can do initially is what is given to you is 100 meter cube per minute. Okay, so that is V dot. And what you can estimate is P1 small v1 equal to RT1. P small v equal to RT. This pressure is known. R is for dry air, which is 287, and T1 is given to us in the problem. So you can estimate the value of this V1, which is in meter cube per kilogram. This is in meter cube per kilogram, and V dot is in meter cube per minute. So this V dot is in meter cube per minute. So if you want to find out M dot, hope now you are aware what we are going to do. M dot is capital V dot divided by small v. So you can say V1 dot divided by small v1. So that will give you M dot 1. So that is the mass flow rate of dry air, and that is in kilogram per minute. Okay. And now what we have to find out is the mass flow rate of oxygen. So how will you find out the mass flow rate of oxygen? One more thing, what is given to us is this T2. T1, T2 is given. So we know H is Cp times T. H is Cp times T. So Cp for air is 1.005 and the temperature is given to us in the problem. So you know the value of H1. Your Cp of oxygen should have been given. It is not given to us in the problem. It should have been given. So Cp of oxygen into temperature of oxygen. So if I'm using subscript, so this is for air. And this is for oxygen. And so we know from what we have done, M dot 1 into H1 energy balance plus M dot 2 into H2 should be equal to M dot 3 into H3. Okay, Cp is not given to us in this particular slide, but definitely we need the value of Cp. So you by knowing the value of Cp of air and Cp of oxygen, H1, H2 is known to us. Because the Cp value is known, you can find the Cp of the mixture using the relation summation of Xi Cpi. Okay. But for that, we need the mass first. but mass is not given to us in the problem. So let's see how they have taken the value of Cp. A very simple relation that they have taken. Hope you are able to understand this. So this is in one stream, m dot air into h air, and this is m dot O2 into HO2. And now these two are mixing together. Okay. So they have simply taken this and put it inside the bracket for the mixture. Okay. And what they have done is they have converted it in terms of temperature. So this becomes Cp times T1, and this becomes Cp times T2. And so this becomes Cp times T3, and this becomes Cp times T3, but for oxygen, and this is for air. And now they have kept the oxygen terms on one side and air terms on the other side, and they have estimated the value of the mass flow rate of oxygen. So that is 23.09 kilogram per minute. Okay. So if m dot O2 is known, then if you add m dot O2 and m dot air, that will give you m dot for the entire mixture. Okay, but that is not asked. So let's not worry about that. And then they are asking us to find the mole fraction of dry air and oxygen in the existing mixture. Now m dot is known to you, and m dot of dry air is known to you. M dot of what is that? Oxygen is known to you. Now you can find out the mole fraction. First, you have to find out the number of moles, which is mass divided by molecular mass. So that will give you the number of moles. And then you have to find out Y equal to number of moles of oxygen divided by number of moles of total number of moles. Okay. So here now, because everything is in dot, so you have kilomole per minute everywhere. Okay. So once you estimate this, then finding out the mole fraction is simple. And they are asking us to find entropy generation, which is nothing but this entropy generation or production is nothing because of the adiabatic mixing. This we have done while we did entropy. In entropy, we said entropy generation, one of the application that we found out was adiabatic mixing of gases. So the entropy generation here is nothing but the change in entropy of air plus the change in entropy of oxygen. It is same as that which we have done before. Okay. So here it is MCP ln of T2 by T1 minus MR. So because you are multiplying it with mass, so that mass is taken outside. Okay. So what you have here is Cp ln of T2 by T1 minus R ln of P1 by P2. Instead of V2 by V1, it is P1 by P2, because if you remember, the pressure here is constant. It's a constant pressure process. Everywhere it is 1 bar. So you can replace V2 by V1 with P1 by P2. So this replacing V2 by V1 with P1 by P2 is not applicable everywhere, only in a constant pressure process. So because it is a constant pressure process, here they have replaced it. Okay, and adding it gives you the entropy generation term. So the total entropy generation is 19.19 kilojoule per kilominute. Sorry, kilojoule per Kelvin minute. Okay,